Have you ever stopped to think about the one part of your car that literally touches the ground? Not the engine, not the fancy suspension, the humble tire. It's the only thing standing between your 2-ton machine and the road beneath it. And yet, most of us never give it a second thought. We obsess over horsepower 0 to 60 times and paint colors, but without those round rubber rings, you're basically sitting in a very expensive paperweight. Tires are often called the soul of movement, and that's not just a poetic phrase tossed around by car enthusiasts. These circular rings of rubber are the silent force behind almost every aspect of driving. They're the reason a Formula One car can carve through a high-speed corner like it's breaking the laws of physics, why a heavy family SUV can stop safely on a rain-soaked highway, and why that long summer road trip doesn't end with you fishtailing into a ditch. Every time you press the accelerator, crank the wheel, or slam the brakes, it's the tires translating all that mechanical power into motion. They dictate how quickly you launch off the line, how confidently you handle a sharp curve, how short your stopping distance is, and even how efficiently your car sips fuel. In short, they're doing far more heavy lifting than most drivers ever give them credit for, quietly shaping every second of your journey from the moment you start the engine. But here's the part that'll blow your mind. Despite being so crucial, a tire starts its life as something that looks nothing like a tire at all. It's not black, it's not round, and it certainly isn't tough. It all begins as a sticky, milky white sap dripping out of a tree thousands of miles away from where you're driving right now. Deep in lush tropical plantations, skilled workers move with almost surgical precision, using sharp practiced cuts to tap rubber trees and release their milky white latex, a natural liquid rubber that's been used for centuries. This sap might look fragile and harmless, but it's the starting point of one of the toughest materials on Earth. Drop by drop, it drips into small cups strapped to the tree, collected over hours in a process that's as much art as science. But on its own, this raw latex is far too soft, too elastic, and nowhere near strong enough to survive the intense heat, pressure, and punishment that tires endure. To make it usable, workers immediately mix it with ammonia to prevent it from spoiling, then concentrate it to boost its strength and stability. The liquid is rolled into thin, flexible sheets, the first real building blocks of a tire, and carefully dried before being shipped off to giant industrial plants where its transformation from tree sap to high-performance engineering marvel truly begins. Now here's where science takes over. Natural rubber is strong, but modern tires demand more durability, more resistance to heat, and more flexibility in freezing cold. That's why it's blended with synthetic rubber, a man-made material created from oil and gas through a process called polymerization. By linking molecules like butadiene and styrene into long chains, engineers build a super strong material that can handle thousands of miles of punishment without breaking a sweat. In fact, more than 60% of a modern tire is synthetic rubber. And if you thought rubber was naturally black, think again. It's actually off-white until manufacturers mix in carbon black, a fine powder that massively boosts strength and wear resistance. They also throw in softening oils to keep the rubber flexible, sulfur to improve bonding, and dozens of other chemical additives that tweak properties like hardness, temperature resistance, and curing speed. More than 30 ingredients are carefully measured and blended in industrial mixers that reach scorching temperatures and massive pressures. After a few minutes, the once white sap is now a thick jet black compound, the backbone of every tire. This compound is then rolled into large sheets and cooled, but we're still miles away from anything resembling the final product. At this stage, the material is strong, but it's just one part of a complex, multi-layered puzzle. The next step is reinforcement, and this is where tire making stops looking like mixing ingredients in a kitchen and starts looking like high-precision engineering. Those thick black rubber sheets that started life as tree sap are now flattened, stretched, and layered with ultra-strong synthetic fabrics, each one carefully coated with rubber and bonded together under intense pressure and heat. You can think of these layers as the skeleton or bones of the tire. They're what give it shape, strength, and the ability to flex without failing. But that's only half the story. Next come the steel belts, hair-thin, high-tensile wires that are meticulously aligned and woven into the structure before being sealed inside the rubber. These belts are like the tire's hidden armor. They help it keep its form at blistering highway speeds, they absorb and distribute impact forces to resist punctures, and they provide the rigidity needed to handle the massive loads that cars, trucks, and even airplanes put on them every single day. Without these reinforcements, a tire would wobble, deform, and wear out in no time. With them, it becomes a precise, load-bearing machine, strong enough to handle thousands of pounds while still flexible enough to grip the road through every twist, turn, and sudden stop. By now, we've got the materials, but they still need to become a tire. That's where the building phase begins. In giant automated assembly lines, robotic arms carefully layer each piece, inner liners, sidewalls, fabric plies, and steel belts onto a large rotating drum. Every layer must be perfectly aligned, pressed, and tensioned. We're talking tolerances within 1/10 of a millimeter. Cameras and sensors monitor every move, while computers make micro adjustments in real time to ensure nothing is out of place. A single mistake here, even a tiny air bubble or misaligned strip, could mean the difference between a safe tire and a catastrophic blowout. Once the raw tire carcass is assembled, it's still soft and shapeless, like a rubber balloon waiting to be inflated. Compressed air is pumped inside to give it its round form, and the structure begins to resemble the familiar donut shape we all know. But it's still missing one crucial feature: the tread. The tread is where rubber meets road, literally. It's the part that grips asphalt, channels water, and provides traction. In smaller factories, the tread might be attached separately at this stage, pressed onto the soft tire shell before curing. But in larger, high-tech plants, the tread is formed during a process called vulcanization, and this is where the magic happens. The unfinished tire is placed inside a two-piece metal mold that's engraved with the exact tread pattern. The mold clamps shut like a giant waffle iron, and then things heat up. Literally, steam or superheated fluid is pumped into a flexible bladder inside the tire, forcing the soft rubber outward until it presses tightly into every groove of the mold. At the same time, the mold is heated to around 160 to 180 degrees Celsius, 320 to 356 degrees Fahrenheit. This heat triggers a chemical reaction between sulfur and the rubber molecules, locking them into a strong elastic network. What was once soft and pliable is now tough, resilient, and ready to handle the road. This process doesn't just give the tire its final shape, it's what gives it its soul. Vulcanization determines how well it grips the road, how much heat it can handle, how long it will last, and how it behaves in extreme conditions. It's the moment when everything, a sense of design, engineering, and chemistry, comes together. But the story of a tire doesn't stop once it leaves the factory or even after it's recycled. In fact, its real journey begins the moment it meets the road, and that's where the hidden science behind those 4 black rings really comes to life. Think about it for a second. Every time you accelerate, brake, or take a sharp turn, those tires are translating mechanical power into motion. They're absorbing impacts, dispersing heat, maintaining grip on dry asphalt and wet roads alike, all while carrying thousands of pounds of weight at highway speeds. And they do this silently, invisibly, without asking for credit. That's why engineers often call tires the translators of a car. Your suspension, engine, and brakes can be cutting edge, but none of it matters if the tires can't deliver that performance to the ground. One of the most fascinating parts of a tire's life is how it changes with use. From the very first mile, its rubber compounds begin to cure even further due to heat cycles. Its tread gradually adapts to your driving style, almost like a custom-fitted shoe. Even the microscopic texture of the tread evolves, developing tiny abrasions and channels that affect how water is dispersed during rain. This constant evolution is why fresh tires feel slightly different after a few hundred miles. They're literally breaking themselves in for peak performance. But this constant contact with the road is also why maintenance matters so much. A tire's performance isn't just about its design, it's about how you care for it. Underinflated tires, for example, flex more than they should, generating excess heat and wearing out faster. Overinflated ones lose contact with the road, reducing grip and increasing stopping distances. Even something as simple as rotating your tires every 5,000 to 8,000 kilometers can make a huge difference. It evens out wear, extends their lifespan, and ensures your car handles consistently no matter the conditions. And let's talk about tread, the part of the tire that directly interacts with the road. Most people only notice it when it's almost gone, but it's arguably the most important safety feature on your entire vehicle. Deep, healthy tread channels water away, reducing the risk of hydroplaning. It provides the biting edges that keep you steady in snow or mud. And on performance cars, the tread pattern is finely tuned to balance cornering grip with straight line stability. Once that tread wears below about 2 millimeters though, its ability to do all that drops dramatically, and so does your safety margin. What's even more incredible is how specialized tires have become. Decades ago, one type of tire had to do everything. Today, there's a tire for every possible scenario. Summer tires use softer rubber for maximum grip on hot pavement. Winter tires stay flexible in freezing conditions and bite into snow and ice. All-terrain tires sacrifice a bit of comfort for the rugged durability needed off-road. And then there's the extreme stuff, like Formula One slicks that heat up to over 100 degrees Celsius in minutes, or run flat tires that can limp you home even after a puncture. Each one is a masterpiece of engineering tailored for a specific job, and yet no matter how advanced the technology becomes, the fundamental principle stays the same. That small patch of rubber, often no larger than the size of your hand, is the only thing keeping your entire vehicle connected to the world beneath it. That's why engineers say tires aren't components, they're lifelines. They're the difference between a controlled stop and a crash, between gripping a corner and skidding off the road. The future of tires is evolving too. Manufacturers are experimenting with airless designs that never go flat, smart tires with embedded sensors that monitor pressure and temperature in real time, and even eco-friendly compounds made from dandelions and recycled plastics. Imagine a future where your car warns you that your tread is wearing unevenly, or where the tire itself adjusts its pressure automatically for maximum efficiency. These aren't science fiction ideas, they're already in development, so the next time you get behind the wheel, think about everything happening beneath you, the chemistry, the physics, the decades of innovation, all condensed into that simple ring of rubber. It's more than just a circle spinning on asphalt. It's the foundation of every journey, the silent partner that turns horsepower into forward motion, and the single most important safety feature your car has. If this deep dive into the secret life of tires gave you a new appreciation for those unsung heroes, there's something almost unreal about the first time you see it. At first, it's just a thin glimmer in the distance, a silver blade rising from an ocean of golden sand. But as you draw closer, it stretches upward endlessly, slicing into the clouds as if it's trying to touch the edge of space itself. That's the Burj Khalifa. More than a building, more than a record breaker. It's a message written in glass and steel, a statement that says, humanity doesn't just build to survive, we build to dream. Yet, for all the headlines about its staggering height, the most extraordinary thing about the Burj isn't how tall it is. It's what covers it. Wrapped around this superstructure is a second skin, a shimmering glass armor designed to battle the elements of the desert. Because here, in a place where summer temperatures soar above 50 degrees Celsius and sunlight hits like a hammer, building tall is one thing. Making it livable is another challenge entirely, and solving that problem would push science, engineering, and design to their absolute limits. To understand how this tower came to exist, you have to rewind to a time before it dominated Dubai's skyline, a time when the city was more ambition than reality. In the early 2000s, Dubai was a rising power with a looming problem. Its wealth still relied heavily on oil, and everyone knew that oil wouldn't last forever. The city needed a new identity, something iconic, something permanent, something that would draw the eyes of the world. So its leaders came up with an idea that bordered on impossible: build the tallest structure humanity had ever dared to imagine. Not just taller than anything that came before, but beautiful, futuristic, and impossible to ignore. Construction began in 2004. 6 years later, the world watched in awe as the Burj Khalifa officially opened, 2,717 feet tall, 163 stories high, and visible from nearly 100 kilometers away. But once the steel and concrete were in place, the real challenge began. How do you protect a structure of that size from the brutal desert climate? How do you create windows that can withstand scorching sunlight, hurricane-force winds, and drastic temperature changes, yet still remain crystal clear for those sweeping views of the Arabian Gulf? The solution began with something that feels almost poetic: sand. The very substance that defines the desert became the starting point for the building's armor. But not just any sand, ultra-pure quartz, mined and refined to perfection. It was mixed with soda ash and limestone in precise, carefully guarded proportions. That mixture was then fed into a furnace the size of a small house, where it was blasted with heat exceeding 2,700 degrees Fahrenheit. Inside, a remarkable transformation took place. The dull, gritty sand melted into a river of glowing orange liquid, molten and alive, flowing like lava. This was the birth of the Burj Khalifa's glass. But turning that molten stream into flawless panels wasn't a simple task. The molten glass was gently poured onto a bed of liquid tin, a process known as float glass manufacturing. Because glass is lighter, it spread perfectly across the tin's surface, forming a smooth, uniform sheet without rollers or imperfections. It was like watching a sheet of liquid light settle into place. Yet even then, the work wasn't done. If the glass cooled too quickly, internal stresses would cause it to shatter under pressure. So it was slowly and carefully cooled in a long tunnel, a process known as annealing, which stabilized its structure and gave it strength. Once cooled, the glass underwent one of the most advanced processes in modern engineering: magnetron sputtering. Inside a vacuum chamber, atoms of silver and other metals were fired onto the surface of the glass, building up invisible layers measured in nanometers. These microscopic coatings completely changed how the glass behaved. They reflected infrared radiation, keeping the desert's brutal heat outside. They blocked ultraviolet rays, protecting the interior from fading and damage. And yet, they still allowed visible light to pour through, filling rooms with natural daylight and preserving the breathtaking views. The transformation continued as the glass was reheated to around 1,150 degrees Fahrenheit and then blasted with cold air, a process called tempering. This rapid temperature shock compressed the surface, making the glass up to 5 times stronger than ordinary windows. And if it ever did break, it would crumble into small, harmless pieces instead of dangerous shards. Finally, 2 sheets of glass, one coated, one laminated, were fused together with a thin spacer in between, forming a sealed cavity. That space became a powerful thermal barrier, locking the heat out and the cool air in. The result wasn't just a window, it was a piece of environmental technology. Of course, creating this advanced glass was only half the battle. Installing it on the tallest building on Earth was another story entirely. Each panel weighed hundreds of pounds, and more than 26,000 of them had to be lifted and attached with millimeter precision, hundreds of meters above the ground. Specialized cranes hoisted the panels into position, while teams of workers, often suspended from harnesses high in the sky, guided them into place. More than 12,000 workers contributed to this monumental task, investing over 22 million hours to assemble the Burj Khalifa's shimmering exterior. And once installed, the glass didn't just sit there, it worked. In Dubai's humid climate, condensation forms naturally on the panels. Most buildings would simply let it evaporate. The Burj Khalifa, however, captures and collects it. The building channels this water into storage tanks, harvesting roughly 15 million gallons every year, enough to water all the gardens surrounding the tower. The structure isn't just standing in the desert, it's interacting with it, turning nature's challenges into resources. What began as sand now acts as a shield, one that reflects light, regulates temperature, blocks radiation, and even gathers water from the air. It's more than glass, it's a living skin, a technological armor that makes it possible for people to live and work comfortably in a place that should, by all logic, be inhospitable. And it's a perfect metaphor for what the Burj Khalifa represents. The idea that human ingenuity can reshape the natural world, bending it into something that serves our ambitions instead of standing in our way. But the story of the Burj Khalifa's glass isn't just about engineering brilliance, it's also about how far humanity is willing to push its own imagination. Because when you peel back the layers of that shimmering facade, what you're really looking at is a philosophy, one that's repeated across countless industries and inventions. It's the idea that raw, messy materials from nature can be transformed into something refined, purposeful, and world-changing. We've done it for centuries. Sand into glass, iron into steel, crude oil into fuel. The pattern is the same. We take what the earth gives us in its most chaotic, unrefined form, and through science and ingenuity, we shape it into something that powers our cities, connects our continents, and redefines what's possible. The Burj Khalifa is just one, albeit spectacular, expression of that story. It's a concept you see clearly when you compare glassmaking to another cornerstone of the modern world, oil refining. Deep in the heart of Texas, vast refineries receive shipments of crude oil, thick, black, and unusable in its natural state. It's heated, distilled, broken apart, and recombined into products that power planes, cars, and industries. It's a transformation that turns a worthless raw substance into the lifeblood of modern civilization. And in many ways, the process mirrors what happens inside a glass plant. Both take elemental resources and, through extraordinary precision, elevate them into something extraordinary. That's the deeper story hiding behind the Burj Khalifa's reflective skin. Each of those 26,000 panels is more than a construction material. It's a triumph of chemistry, physics, and design. It's proof of what happens when thousands of small decisions, the right sand, the right coatings, the right temperature, the right installation techniques come together in perfect harmony. And it's proof that no dream is too ambitious if you're willing to solve 1,000 small problems on the way to achieving it. Every detail of the Burj Khalifa's design reflects this mindset. Even its Y-shaped floor plan, inspired by a desert flower, is about more than aesthetics. It channels wind around the structure, reducing pressure and preventing the kind of vortex shedding that could make a tower sway or vibrate uncontrollably. The building doesn't just resist the elements, it collaborates with them, shaping and redirecting their forces. The same principle applies to the glass. Its coatings don't merely block sunlight, they manipulate it. Infrared wavelengths are reflected outward, ultraviolet light is filtered, and visible light is diffused in just the right way to illuminate the interiors without overheating them. The panels don't just stand there passively, they're actively working every second of every day to maintain the tower's delicate internal environment. And while they're doing that, they're also collecting and redirecting water, millions of gallons of it each year. What would otherwise evaporate into the desert air is captured and put to use, watering the landscaped gardens that surround the tower and softening the harshness of the environment. This isn't just clever engineering, it's a subtle form of sustainability. In a region where water scarcity is a daily concern, the Burj Khalifa quietly demonstrates how even the most iconic structures can help sustain the ecosystem around them. That attention to detail extends far beyond the materials themselves. The installation of the glass panels was a logistical operation as complex as the Apollo missions. Each panel had to be manufactured, shipped, lifted, and secured in an order so precise that even a single mistake could compromise the building's performance. Wind loads, thermal expansion, alignment tolerances, every variable was calculated down to fractions of a millimeter. The result is a facade that isn't just strong and beautiful, but perfectly integrated into the building's structural system. And perhaps the most fascinating part, even after all these years, the Burj Khalifa's glass is still doing exactly what it was designed to do, and doing it flawlessly. The tower remains cool and habitable in one of the hottest climates on Earth. Its interior spaces are flooded with natural light without becoming ovens. Its reflective surface still gleams under the desert sun, as striking now as it was on the day it opened. When people visit the observation deck and gaze out over Dubai's skyline, they're usually thinking about the view, about the sheer height, the endless city below, the Persian Gulf stretching into the horizon. What they don't realize is that the only reason they can stand there comfortably, hundreds of meters above the ground, is because of the invisible science all around them. Every ray of sunlight they see, every gust of hot desert wind that never makes it inside, every drop of condensation that's quietly collected, all of it is the result of deliberate, meticulous choices made decades earlier. And that's the deeper beauty of the Burj Khalifa story. It's not just a tale about building the tallest tower. It's about humanity's refusal to accept the limitations of nature as they are. It's about solving problems that once seemed unsolvable, not by brute force, but by creativity, precision, and persistence. It's about looking at something as simple as sand and deciding it can become something extraordinary. When the Burj Khalifa opened in 2010, it was hailed as a symbol of wealth and ambition. But if you look closer, you see something much bigger. You see the fingerprints of thousands of people across continents, scientists, engineers, designers, and workers, each contributing their expertise to a single vision. You see the fusion of ancient knowledge and cutting-edge technology. You see a structure that doesn't just defy gravity, but also climate, physics, and time. And perhaps most importantly, you see a promise. A promise that no matter how extreme the environment, how audacious the dream, or how impossible the goal, there's always a way forward if we're willing to innovate. The Burj Khalifa isn't just a skyscraper, it's a testament to what humanity can achieve when ambition meets ingenuity. So the next time you see that iconic spire gleaming against the desert sky, don't just think of it as the tallest building in the world. Think of it as a story told in glass. A story of transformation, collaboration, and relentless curiosity. Think of the sand that became glass, the glass that became armor, and the armor that became a beacon of possibility. Because in the end, that's what the Burj Khalifa truly is. Proof that the impossible isn't a wall, it's a starting line. If stories like this fascinate you, the ones hidden beneath glass and steel, where science meets imagination and engineering turns into art, then don't stop here. In a world of roaring engines and the constant push for speed, there is a moment of silent, absolute necessity. The moment you need to stop. That critical transition from unchecked momentum to controlled safety hinges on a component that works in the shadows, enduring immense forces, transforming violent kinetic energy into dissipating heat thousands of times over its life. This is the story of the unsung hero of motorcycle performance and safety. The brake disc. Today, we venture inside the high-tech heart of modern manufacturing to unravel the precise, step-by-step journey of how a motorcycle brake disc is made, from a pile of raw, earthy materials to a gleaming, life-saving piece of engineered perfection. Our story begins not on the factory floor, but in the science of metallurgy. The soul of a brake disc is its material. For the vast majority of motorcycles, from daily commuters to apex hunting sport bikes, that material is a special high-carbon alloy of cast iron, often a grade known as G3000, or a high-silicon molybdenum iron. This is no ordinary iron, it is a carefully formulated recipe, a secret blend for many manufacturers, chosen for a sacred trio of properties: excellent thermal conductivity to carry heat away from the pad contact zone, inherent wear resistance for longevity, and most crucially, a high and consistent coefficient of friction to provide that predictable, firm bite every time the lever is pulled. The raw ingredients, piles of recycled steel scrap, primary pig iron, and precise alloys like ferrosilicon and ferromolybdenum are gathered. Computer-controlled scales measure each component down to the gram, because consistency here is the foundation of safety. A single percentage point's deviation in carbon or silicon can alter the disc's very character under the extreme stress of braking. This meticulously weighed charge is then fed into the mouth of a roaring furnace. Within, temperatures skyrocket past 1,500 degrees Celsius, over 2,700 degrees Fahrenheit, reducing the solid metal into a bubbling, glowing crucible of liquid potential. This is a vat of pure molten transformation. Before the pour, a sample is taken, cooled, and analyzed by a spectrograph. This machine reads the elemental signature of the metal, confirming the chemistry is perfect, ensuring batch after batch will perform identically. While the metal reaches its liquid state, its future shape is being prepared in another part of the foundry. Here, automated molding machines create the disc's negative image from resin-bonded sand. The molds are formed in two halves, known as the cope and drag. The cavity inside is simple but definitive. It will form the disc as blank, the rough as-cast shape that holds the promise of the final product. The moment of truth arrives with a stream of incandescent orange metal. The furnace tilts, and the molten iron flows like luminous honey into the waiting sprue of the sand mold, filling every contour. As it solidifies, a key microscopic event occurs. The carbon within the iron forms into graphite flakes. This unique structure, inherent to gray iron, is what grants the material its excellent damping characteristics, its ability to absorb vibration, and its relative ease of machining later on. The filled molds travel down a cooling line, the fierce glow within them fading slowly from yellow to cherry red, and finally to a dull black over several hours. Once cool, they reach a shaking station. The molds vibrate violently, and the sand shell fractures and falls away, revealing the newborn brake disc castings within. They emerge as dark, rough objects, covered in a fine scale of oxidation, with lumps of excess metal. The gates and risers that fed the molten flow still attached. They bear only a faint primordial resemblance to the finished part. This is where the art of subtraction begins, where precision engineering sculpts the rough form into a geometrically perfect component. The castings, now called blanks, are transported to a clean, well-lit machining hall. The first stop is almost always a CNC lathe. A worker clamps a rough blank onto the lathe's chuck. With a command, the machine whirs to life. The blank begins to spin, and a sharp carbide cutting tool approaches. On contact, a tight continuous spiral of dark iron swarf peels away, and beneath it is revealed a smooth, shiny silver surface. This is the first act of creation through removal. The lathe's primary mission is to establish the disc's critical reference surfaces. It machines the mounting face, the precise surface that will bolt directly to the motorcycle's wheel hub, to an exacting flatness, often within a few hundredths of a millimeter. It also turns the outer diameter and begins to skim the two faces that will become the braking surfaces. This initial machining ensures the disc will run true, without axial or radial runout, wobble, when finally installed. From the lathe, the disc often travels to a multi-axis machining center. Here, the transformation becomes more intricate. Drill bits whirl to life, cutting the exact pattern of mounting bolt holes with robotic precision. End mills trace paths, machining the internal splines or the carrier screw holes, and carving any aesthetic contours or lightening pockets into the inner bell section of the disc. For high-performance floating discs, this stage is where the separate aluminum center carrier or hat is also machined, and the precise slots for the floating buttons or bobbins are cut. Now, we create the disc's signature, its functional fingerprint. Before any holes are added, many discs receive a pattern of shallow curved grooves machined into the friction surface. These are often called scrub lines or conditioning grooves. They are not merely decorative. Their purpose is to gently scuff the surface of new brake pads during the critical bedding in process, optimizing contact and heat transfer from the very first stop. They also serve as microscopic channels to clear away water, fine debris, and combat pad glazing. For performance and premium street applications, the next step defines the disc's appearance and advanced functionality, drilling and slotting. A plain machined disc is mounted onto a massive CNC-controlled drill press. Above it, a solid carbide drill bit, engineered for the task, rotates at high speed. In a shower of sparks and a sharp metallic whine, it plunges through the iron, emerging cleanly on the other side to create a perfect round hole. This process is repeated hundreds of times in a precise pattern across the entire friction ring. This is cross-drilling. The reasons are deeply engineered. First, heat dissipation. The holes massively increase the surface area of the disc, acting like tiny radiators to pull heat out of the mass and radiate it away into the passing air. Second, weight reduction. Removing this material lightens the unsprung weight and the rotating mass, improving suspension response and acceleration. Third, and vitally, they provide an escape route for gases. Under extreme heat, brake pads can release gases. If trapped between the pad and disc, these gases can create a lubricating layer, leading to a sudden loss of braking power known as gas fade. The holes vent these gases away, maintaining consistent pedal or lever feel. Alongside, or sometimes in place of holes, come slots. Using a thin grinding wheel or slitting saw, radial channels are cut from near the disc's inner radius out towards its edge. These slots perform a similar duty, but are particularly aggressive at scrubbing the pad surface clean, constantly wiping away glazing and maintaining a high-friction interface. They also play a strategic role in heat management by providing controlled paths for thermal expansion, helping to prevent the random, dangerous stress cracks that can form in a solid, overheated disc. Think of a disc under the immense thermal load of a racetrack or a long mountain descent. A solid disc can develop concentrated hotspots, leading to uneven pad transfer, warping, and fading performance. A drilled and slotted disc, by its very design, distributes that heat more evenly across its entire area. The holes and slots break up the heat patterns, preventing localized thermal crises and maintaining consistent, predictable stopping power. After the aggressive machining operations, the disc requires refinement and strengthening. It enters a shot-blasting cabinet. Inside, it is bombarded by millions of small, hard steel beads propelled at high pressure. The cacophonous ringing is the sound of transformation. This process does more than clean off residual scale. It hardens the very surface of the metal, improving its wear resistance, and it creates a uniform, matte gray surface texture that is ideal for the next step. Most critically, it acts as a final inspection, as any hidden casting flaw or subsurface weakness will often be revealed by the blasting process. For many performance-oriented discs, the next step is a journey through a furnace for heat treatment. This is not to harden the iron like steel, but to anneal it, to stress relieve it. The discs are slowly heated to a specific temperature in a controlled atmosphere, held there to allow the internal atomic structure to relax, and then cooled at a prescribed rate. This meticulous thermal cycle releases the internal stresses locked into the metal from the violent cooling of casting and the pressures of machining. The result is a disc that is dimensionally stable, far less prone to warping under the wild thermal cycles of hard use, and one with a more uniform internal grain structure for ultimate durability and consistency. With its form finalized and its structure stabilized, the disc must now achieve perfect harmony. Every single brake disc undergoes dynamic balancing. Placed on a machine similar to a wheel balancer, the disc is spun at a high speed. Sensitive sensors detect the slightest imbalance, a heavy spot that would cause a minute but intolerable vibration at the wheel. A monitor displays a spike on a graph pinpointing the location of the excess mass. The solution is elegant and minimal. On the inner bell section, well away from any critical stress areas or friction surfaces, a small precision drill takes a shallow divot out of the metal, removing just a few grams of material. The disc is spun again. The graph now shows a smooth line. The imbalance is corrected. This ensures that at highway speeds, the rider feels only smooth rotation, not a dangerous handlebar shaking tremor. The final stage is about protection and preservation. To defend against its eternal enemy, corrosion, the disc receives a protective coating. The discs, hanging from an overhead conveyor, descend into a bath of a special chemical solution, often a black oxide or zinc phosphate process. This is not a paint that sits on top, it is a conversion coating. The chemicals react with the iron itself, creating a new molecularly bonded layer of magnetite on the surface. The disc emerges with a deep, consistent matte black finish. This coating is tough and corrosion-resistant, protecting the intricate drilled holes and the inner bell from rust, especially from road salts and weather. Every disc is also given a final, meticulous visual inspection by trained human eyes, looking for any imperfection in the machining, coating, or structure. Only the discs that pass every single test without compromise are allowed to proceed. These packages are stacked on pallets, ready for shipment to the assembly lines of major motorcycle manufacturers or to the warehouses of aftermarket performance parts distributors. So the next time you ride and you gently squeeze that brake lever, feeling the motorcycle slow with obedient, confident authority, it is a masterpiece of applied physics, materials science, and manufacturing rigor, all dedicated to one simple, vital purpose. Every single year, over 30 million tons of bamboo are harvested across the world. That's more than the combined weight of all the commercial airplanes ever built. But bamboo isn't just any plant. In fact, it's not even technically a tree, it's a grass. And not just any grass. This is the grass that can take on steel, silk, and even concrete. It's a plant that can grow taller than a giraffe in a matter of weeks, absorb more carbon dioxide than a forest, and regenerate itself without anyone planting a single seed. Bamboo isn't just another green stem waving in the wind. It's a green giant quietly revolutionizing industries, from construction to fashion. And this journey begins in places where acres of these towering stalks stretch as far as the eye can see. These aren't wild, overgrown thickets. Bamboo plantations are carefully managed, functioning more like sustainable farms than forests. Unlike trees that take decades to mature, bamboo grows rapidly and regenerates naturally. When a stalk, known as a culm, is cut, it doesn't need to be replanted. Thanks to its underground rhizome network, new shoots sprout almost immediately, allowing the same plantation to produce for decades without exhausting the soil. Bamboo stands out not just for its growth, but for its environmental benefits. It absorbs 35% more carbon dioxide and produces 35% more oxygen than an equal area of trees, making it a powerful ally in the fight against climate change. It thrives without chemical fertilizers or replanting, making it one of the most renewable resources on Earth. Harvesting bamboo is a precise task. Only mature stalks, aged 3 to 5 years, are selected based on color and texture. Workers use machetes or handsaws to cut them, leaving younger shoots untouched to continue the cycle. These towering stalks, sometimes 60 feet tall and weighing over 100 pounds, are then transported, often by hand-loaded trucks, to processing plants. What happens next is an industrial transformation that turns this green giant into flooring, fabrics, and so much more. The journey of bamboo from stalk to product begins with chopping down the towering green culms into smaller, manageable pieces. These sections are then fed into powerful machines that split the rounded stalks into flat, usable strips, each one cracking open with a loud, unmistakable snap. This is the moment when bamboo stops looking like a wild plant and starts to resemble a raw material ready for engineering. But raw bamboo isn't ready for use just yet. The outer green skin and inner nodes must be stripped away, revealing a pale plank underneath. However, inside that plank are sugars and starches, exactly what mold, fungi, and insects love. To make bamboo last, these must be removed. The planks are soaked in large vats filled with boiling water or hydrogen peroxide, a sterilizing bath that kills bacteria, draws out sugars, and leaves the bamboo clean. Moisture is the next challenge. Raw bamboo holds up to 50% moisture, so it goes into industrial kiln dryers until that level drops to a stable 8 to 10%. Once dried, it's milled into perfect rectangles. These planks can be laid flat for horizontal flooring or turned on their edge for denser vertical flooring. But strand-woven bamboo goes further. The bamboo is shredded into fibers, mixed with eco-resin, and pressed under 3,000 psi. The result? A block of material that can score over 5,000 on the Jonka hardness scale, far tougher than oak. Surprisingly, bamboo also transforms into ultra-soft fabric. Ground into pulp, chemically treated into viscose, and extruded through fine nozzles into acid baths, it becomes silky, breathable thread. That thread is then spun into fabric that's hypoallergenic, antibacterial, and perfect for everything from clothing to bedding. From hard as oak to soft as silk, bamboo truly does it all. Bamboo's dual nature, strong as steel yet soft as silk, has made it a favorite across industries. It's in cutting boards, textiles, scaffolding, and even luxury car interiors. What makes it extraordinary is that it grows faster than any tree, needs no chemicals, and regenerates on its own. From paper and furniture to biomass fuel and construction, bamboo is everywhere. With over 1,000 species suited to different climates and uses, it's cultivated globally, from Asia to Africa and South America. The bamboo industry is now worth over $100 billion and continues to grow. Whether it's scaffolding that bends without breaking or sleek, sustainable flooring, bamboo blends beauty, strength, and environmental responsibility into one incredible, fast-growing solution. Then there's strand-woven flooring, which is so tough that it's used in high-traffic commercial spaces like offices, museums, and even airports. Try dragging furniture across that and see if it leaves a mark. It probably won't. And even if it does, a quick sanding can bring the surface back to life. Bamboo is making quiet moves in the industrial world. Inside premium cars, interior panels made from bamboo composites offer lightweight strength and natural beauty, even helping dampen sound. This blend of sustainability and luxury is becoming the new norm. Beyond that, bamboo fibers appear in surprising places. From toothbrush bristles to structural supports in eco-friendly buildings, it's found in biodegradable straws, sleek furniture, and countless products born from innovation. But bamboo's transformation isn't magic. It's a process. One critical step is drying. Done wrong, it can ruin the material. Done right, it ensures strength and durability. Industrial dryers lower moisture from 50% to around 8 to 10%, stabilizing the bamboo for long-term use. Unlike hardwood trees, which take decades to grow and require replanting, bamboo regenerates from its roots. No soil damage, no clear-cutting, no erosion. It simply regrows, making it a champion of sustainability. Properly managed bamboo farms improve soil health, fight climate change by absorbing more carbon dioxide than trees, and support livelihoods without harming ecosystems. It's not just what bamboo becomes, it's how responsibly it gets there that makes it so powerful. On bamboo plantations, local workers often blend traditional harvesting knowledge with modern tools. They carefully select only mature stalks while leaving the young shoots untouched, allowing the cycle to continue uninterrupted. This selective approach keeps the plant regenerating naturally and ensures a long-term sustainable harvest. And there's more innovation on the horizon. Scientists and designers are exploring bamboo's potential in fields like bioplastics, composites, and even medical materials. Experiments are underway to use bamboo fibers in prosthetics, surgical tools, and packaging materials that decompose naturally. No more plastics clogging the oceans. It's no longer just about what bamboo is, it's about what it could become. And the most exciting thing is that this isn't some far-off dream. It's already happening. Of course, none of this works without people, skilled workers across the world, from farmers to technicians to designers, all contributing to the transformation of this humble stalk into a global force. On the plantations, people still walk among rows of towering culms with nothing but machetes, relying on generations of knowledge to choose the right ones to cut. In the factories, workers guide planks into machines that split, shave, boil, and bake them into form. And in the design studios, visionaries imagine what else bamboo can be. Shoes, sunglasses, bicycles, kitchenware, maybe even the next wave of electric vehicle interiors. Every link in the chain matters, and every step reflects how far bamboo has come, from a regional resource to a global game changer. And yet, for all its innovation, bamboo remains humble. It doesn't require fanfare. It just grows, quietly, efficiently, and incredibly fast. In the right climate, you can actually hear it grow. Some species can shoot up nearly a meter in 24 hours, making them the fastest growing plants on Earth. That kind of growth isn't just impressive, it's game-changing in a world where time and resources are running out. And here's a surprising fact: bamboo is technically a type of grass. Despite its woody appearance and towering height, it's closer to the grass in your lawn than the oak tree in your backyard. But unlike grass, bamboo doesn't stop at a few inches. It keeps going, 30, 40, even 60 feet into the air. And with over 1,000 species, there's a bamboo for just about every purpose, from the tiny ornamental types that decorate living rooms to the giants used for timber and construction. Still, managing this incredible resource takes knowledge. You can't just plant bamboo and walk away. Farmers must know which variety works best for their climate, how to space the culms, when to harvest, and how to care for the rhizome system. With proper care, a single bamboo plantation can provide sustainable harvests for decades. It's the gift that keeps on giving, literally. Now picture this. A factory receives a truckload of 60-foot bamboo stalks. They're green, rough, and full of moisture. By the time they leave the facility, they've been cleaned, stripped, sterilized, dried, pressed, and shaped into products as varied as luxury flooring, soft towels, strong scaffolding, or smooth fabric. It's a full-circle transformation, and it all starts with that first clean cut on the plantation. Now, here's the kicker. The bamboo market is already a giant, and it's only getting bigger. Industry forecasts suggest that the global bamboo economy is heading toward a valuation of over $100 billion. And it's not a bubble, it's a steady climb, powered by real demand, practical innovation, and undeniable sustainability. And while other materials rely heavily on mining, deforestation, or chemical processing, bamboo relies mostly on sunlight, water, and time. That's it. No synthetic inputs, no massive replanting campaigns, just a network of underground roots doing what they do best, regrowing. So what's the catch? There really isn't one as long as plantations are responsibly managed. Overharvesting, monoculture farming, and illegal clearing of natural forests to make room for bamboo crops are real concerns. But with the right balance and oversight, bamboo remains one of the most sustainable resources humans have access to. The story of bamboo is a story of nature's engineering. One plant, fast, strong, beautiful, and versatile, quietly transforming the way we build, dress, furnish, and even heal. And it's just getting started. By now, it's clear that bamboo isn't just a plant, it's a strategy. Nature's blueprint for a better way to build, live, and create. In a time when nearly every industry is rethinking how to cut emissions, reduce waste, and protect the planet, bamboo offers not just an alternative, but a solution that's already proving itself on a massive scale. Every year, over 30 million tons of bamboo are harvested around the world. That's not just a number, it's a reflection of just how deeply bamboo has rooted itself into our modern world. And the growth doesn't stop there. With urban centers expanding, demand for sustainable construction materials rising, and consumer expectations shifting toward eco-conscious products, bamboo is set to play an even bigger role in everyday life. And the beauty of it all? Bamboo doesn't ask much in return. It doesn't demand harsh chemicals. It doesn't ruin the soil. It doesn't even need to be replanted after harvest. It simply grows, renews, and gives back more than it takes. Choosing bamboo over traditional materials sets off a powerful ripple effect. When designers opt for bamboo flooring, they help preserve forests by avoiding the need to cut down trees that took decades to grow. When fashion brands embrace bamboo fabrics, they offer soft, breathable, biodegradable clothing that's gentle on sensitive skin. And when cities use bamboo in construction, they're investing in structures that are both strong and sustainable. Bamboo also brings real-world benefits to communities. It creates jobs in farming, processing, manufacturing, and design, especially in rural areas, while also powering innovation in modern industries. It's not just a fast-growing plant, it's a fast-growing opportunity. But here's what really sets bamboo apart. Hidden inside its fibers is a natural strength-to-weight ratio comparable to steel, flexibility under pressure, and resistance to pests and bacteria. These aren't man-made features, they're natural. Bamboo blends ancient tradition with cutting-edge potential. From scaffolding in Hong Kong to high-end flooring in Europe and eco-luxury fashion in New York, bamboo delivers function, beauty, and sustainability without compromise. It's not just a material, it's a message that we can live smarter, build cleaner, grow without destruction. So the next time bamboo shows up in your life, remember, it's not just good for something, it's good for everything. And now, if you made it this far into the story of the world's most extraordinary grass, there's one last step you can take. Hit that like button if you learned something new. Subscribe to the channel for more deep dives into the incredible materials shaping our future. Don't forget to tap the bell so you never miss the next story like this one.